Okay, welcome Frosh. This is my third video in a series going over some midterm review for you, like you all voted for. This is going to be our third question and our last question that we go over, which covers functions and subspaces. I do want to give a disclaimer. This review is not, completely covering every single thing you have to study for the exam. You should be doing other studying, but I think this will give you a good direction on intuition to help solve some of these problems. So we're going to talk about functions and subspaces in the same video. These are both a little bit complex, but essentially most of the questions work exactly the same way. So going over the first question here, we have that C infinity, which is essentially the vector space of functions from R to R that can be differentiated arbitrarily many times. This is an idea of like a smooth function. You can infinitely differentiate or integrate, I think. And, your function will still be smooth. It will still be continuous. You can still take the derivative no matter where. And this is a vector space. You could check that, but obviously we're not going to. You could think of some of the ideas of linearity, for example, like of the integral. If you have the integral of f of g, where f and g are both functions, then that's going to be the same as the integral of f plus the integral of g. So you have the same idea of linearity, where you can split components based on operations, essentially. And we're being asked here, we're given a set. Eventually we're going to prove if W is a subspace or not. But right now we're just simply going to prove if we have these two functions, f1 and f2, that are certainly continuous. You can infinitely take the derivative of cosine, or you can infinitely take the derivative of this exponential here. We're going to see if these are elements of our set W, where W is simply just a rule on our vector space. In this case, it would be a subset, because every single function that abides by this equation here, this differential equation, where the second derivative of f is really equal to the first derivative of f plus 2 times the function itself. That's a subspace of these smooth functions. So we want to know if f1 and f2 are even in our set itself. And then we'll talk about subspaces. So since this is a set rule, we want to see if f1 and f2 are in W. We can essentially just check based on the rule. So over here, I have the setup here, where we have f1 is e to the 2x plus 3 times e to the negative x, and f2 is cos of x. So we're simply going to take the derivative, which for f1 of x is something like 2 times e to the 2x minus 3 times e to the negative x. And then our second derivative here is something like 4 times e to the 2x plus 3 times e to the x minus x. I hope all of you followed that. If not, definitely review. You might be cooked. Okay, so now we're just checking our rule. So is it true that f1 prime prime is equal to f1 prime plus 2 times f1? So that's equivalent to when we just plug all this stuff in. So our f1 prime prime is 4 times e to the 2x plus 3 times e to the minus x. Is that equal to 2 times e to the 2x minus 3 times e to the minus x plus 2 times our original function, which is something like e to the 2x plus 3e to the minus x. Okay, now we're just going to distribute and see if these are the same. So we have 2 times e to the 2x minus 3 times e to the minus x plus 2 times e to the 2x plus 6 times e to the minus x. Now we can simply just group like terms. So we have 4e to the 2x, by adding these two coefficients. And then we have these two exponentials with the same base, so we can add their coefficients as well. And this is going to be something like plus 3 times e to the minus x. Now, this is our left-hand side over here. And then we have our right-hand side over here, which is exactly the same, okay? So we proved that f1 is in fact an element of W. So this implies f1 is an element of W. So f1 is a smooth function, and it also abides by our set rule. Okay? Now we're going to check the same for f2. So f2 is equal to cos of x. Its first derivative will simply be minus sine of x, and its second derivative will be minus cos of x. Now, does this abide by our rule? Our rule is f2 double prime is equal to f2 prime plus 2 times f2, which is equivalent to, simply by substitution, minus cos of x should be equal to, what is it? Negative sine of x plus 2 times cos of x. Now, at least personally, this doesn't look like it's going to work out. We can move some stuff to the other side and see what it's saying. So this would be like equivalent to minus 3 cos of x is equal to minus sine of x. Since these are functions, these should be holding for our whole domain, which is all x, which are real numbers. And we're ending up with a final equation where we should have something like, we can just drop the minus sign because it's on both sides. 3 times cos x should be equal sine of x. Now, since cos and x are the same exact function, just shifted from each other, I think it's pretty clear that if we check, like, at x equals 0, if this is true, that would give us that 3 times cos of x is 1, sine of x is 0. We clearly do not have 3 equal to 0. Therefore, we'll just add it up here. Sorry for being a little messy here, but so f1 is an element of x, and f2 is not an element of W. Okay, so we just proved, some basic stuff. Are these functions even within our subspace or not? Now what we're going to do is we're going to talk about how do we actually prove generally if something's a subspace. So as a reminder, a subspace W, like the one in our question here, are a closed subset of another vector space. And there's 3 criteria where you have to be a subspace. I actually don't know exactly if this part's true. But essentially, you want to show that it's closed under the operations of the space at the very least. And this simply is checking 3 different criteria. The first one is the 0 vector in your space? And this is the same 0 vector from your original space, okay? You can think of it as this picture I drew here. So if we're in the 2D plane, if we're in R2 over here, we can take subsets of this that are just one-dimensional, or that are like, a line within the space, right? The whole idea of linear algebra is you can describe lines very well. So if we have 2 lines here in our R2 space, we have one W2. This is some rule. This is some rule on some set. But clearly, W does not go through the critical origin here, which is our 0 vector in R2. So that would make W2 not a subspace. But since our line W1 is within this space, and it intersects with the origin, there's clear that the 0 vector is here. Okay. So essentially, we need to show that the 0 vector is there, and then next, we need to show that our space is closed under our operations. So we do this in the arbitrary case, as we just talked about with proofs. So essentially, you want to assume that you have any vectors in your space, any W1 and W2 in W, and you want to also show that W1 plus W2 is now still in W. So you don't want to be in a space and then add things within your space and end up outside your space. That would make no sense, right? That's not the point of being in a space. We want to say concretely, all of our operations, all of our math is taking place in this vector space W. And similarly, we want to be closed under scalar multiplication. So for any vector in our space and any real number, we should be able to multiply these two and end up with another vector in our space. Now this also a bit shows the intuition on like why we need the 0 vector, because 0 is simply an element of the real numbers. And we also have this relation where 0 times a vector should be equal to the 0 vector. So if we don't have the scalar multiplication closure, we certainly do not have the 0 vector. And we also can't do any of the operations that we would normally do. Okay, so diving in how we actually prove this, let's give it a try. So we have, our space W, and we want to know if W is a subspace of these smooth real valued functions. So let's check if the 0 vector is here. Since we're in functional space, you can think of this as like the 0 function of x, where everything should be sent to 0. So I guess as motivation for why the zero function of x should be an element of the infinitely differentiable functions, we could prove this inductively. I think that's a little more difficult and probably out of the scope of this. But essentially, the derivative of 0 is always 0. So you can just prove that you can infinitely differentiate, this 0 function, I believe, and thus our 0 function is an element of infinitely differentiable real valued functions. Okay. Next, we want to show closure under our vector addition operation. Now, since we're in like a functional space, you can think of it as like function addition. But thankfully, functions are linear, as we'll see pretty easily. So we're going to say let G1 and G2 be elements of W, and we want to show that G1, so we want to show that G1 plus G2 is an element of our vector space as well. So G1 simply needs to be in the form, to be in W, it needs to be in the form of G double prime is equal to G prime plus 2 times G, and G2 needs to abide by the rule that, these should be G1s, that G2 double prime is equal to G2 prime plus 2 times G2. Okay, now I'm going to use a form of both of these that are just like all on the same side so we can set them equal to each other, because theoretically, you move everything to the left side for both, you're going to have G1 double prime minus G1 prime minus 2 G1 is equal to 0. Our other one's going to be equal to 0. We can set them equal to each other and see how that works. So adding G1 and G2, we're going to have something like, or we could honestly just do it element-wise too, which was maybe what we'll do instead. So we can just add both sides of these and see what happens. So we want to see if G1 plus G2 is in our space. We're going to have something like G1 double prime plus G2 double prime is equal to G1 prime plus 2 times G1 plus G2 prime plus 2 times G2. Now, as we were talking about before, with like the linearity of the integral operator, we also have the linearity of the derivative operator. So we have the derivative of two functions, f and g, like we had before, and they're simply added together. I believe we can just say that this is the same as, d by dx of our function plus d by dx of our other function. So the whole reason this works is because these operations, these integrals and derivatives are linear themselves. So they work within our linear space. So we're going to have something, we can just like almost factor out the derivative in this case. Because we have smooth functions and you can infinitely differentiate them, we're definitely going to have this linearity. Okay, so I guess I should be justifying this a little more as I've been talking about. So we have this case over here, I guess by smoothness of G1 and G2, which is infinite differentiability, and so by our smoothness and linearity of this differential form operator, because you can think of it as like you're used to operations, especially in a vector space, of addition and vector addition and scalar multiplication. But you can also have other linear operators, and as I was just talking about, there's this idea of linearity of our differentiation. So we can simply draw out these almost like factoring out our differentiation simply because this is linear and it distributes linearly across our vector addition here. Okay, so I justified it. We can just simply, do our similar factoring that we always do. And we have something like this after we're done factoring. So the derivative, or the second derivative of g1 plus g2 is equal to the first derivative of g1 plus g2, which is equal to, or when added together with 2 times g1 plus g2. So this is exactly our rule for w. So we basically just showed that for any arbitrary g1 and g2 that are elements of w, when we take g1 plus g2, that's also an element of w. And I should also say that the reason we're simply able to go from like this step over here to combining them linearly over here is because we're in a linear vector space. We can do these linear operations. We have homogeneity of our operations as well. So, okay. We've now proven that we have this like closure argument under vector addition in our functional vector space. We have the zero vector. Now we only need to show, is this closed under scalar multiplication? Oh, just found out this is with an A. Okay, so what's the definition of being closed under scalar multiplication? This means that we have, a real valued scalar alpha and a vector in our vector space. Now these are both arbitrary. We want to now see if alpha times w is an element of our vector space. Okay, so we have this w in w. I guess w is going to be our function. So also, I wasn't clear about this before, but these are g's acting on x. They have some input. They have some value. And that's why, like here, for example, we were able to show by counterexample that if we just choose an x value of 0, our equation doesn't hold, we're not in w, and therefore f2 was not an element of w. Okay, so w1 has to be in the form of w's second derivative being equal to w's first derivative plus 2 times w. Now we're going to see what happens when we take alpha times this. Once again, we could move things to the other side, or we can just cleanly multiply alpha by our rule and then see if it still abides by our rule. So alpha, we're trying to show if now alpha w abides by this rule. Now what does alpha w look like? That looks something like this. The second derivative of alpha w is equal to alpha w plus 2 times alpha w. All right? I believe this is enough. There is a case where you should maybe be showing this, but I'm pretty sure they're just equivalent in our vector space. Okay, so yeah, yell at me if that one's wrong. I don't know. Check the solutions. I haven't really. So anyways, by our same linearity argument, like when we have the derivative of 2 times e to the 2x, for example, that we were doing earlier, this is the same as 2 times the derivative operator acting on e to the 2x, essentially, right? We have this linearity where we can bring constants out to the front. Maybe we haven't thought about it in terms of linearity, but that's what that operation is. We can move scalar valued real numbers outside of our functions and still get the exact same derivative. And that's simply what we're going to do. So this is alpha times w squared, the second derivative of w, and then we have alpha times the first derivative of w times 2 times alpha times w. Now, what this looks like to me is we assumed that we have w in our space and alpha is a real number, and we just showed that I guess you could also just choose something like, maybe you should specify alpha is non-zero here, and then you can divide out by alpha, where you have W double prime is equal to W prime plus 2 times alpha. Okay? Because we want to see if this holds for all alphas. It clearly holds for alpha is equal to 0. That's just like the trivial case where if 0 is equal to 0 plus 0. Okay? So essentially, given scalars and a vector in our space, what happens when we multiply these together? Are we still in our space? I think it's clear that we're still abiding by our W rule, and that means that alpha times W is an element of W. Okay? Now to wrap everything up, therefore, we have the 0 function is an element of our subset. We have that for all W1 and W2 in our subspace, or in our subset, and for all W1 and W2, that implies that W1 plus W2 is also an element of our subset. And we also have, for all regular functions that are in our space, and all real number scalar values, we have that alpha W is also an element of our vector space. So thus, W is a valid subspace of C infinity, or the infinitely differentiable real valued functions, and thus we are done. We have proven, I, double I, and triple I. 1, 2, 3. We have proven the three criteria that are necessary to being a subspace. Now we did this through functions. Functions are a little different from our usual space, so instead of showing we have the 0 vector, we need to show we have the 0 function, which maps every element to 0. Now we did this a little loosely. We also showed we have closure under our vector addition simply by the linearity of the thing in our vector space. So the reason that C infinity is a vector space is because at the end of the day, the derivative is a linear operator. What's the derivative? You're finding the tangent line to a curve. So if you're finding a line and you can move scalars in and out, you can split the derivative when you're adding functions to just be applied to each of the functions. That means we have this linearity property that works in a vector space. And then we showed that it's closed under our two operations. It contains the 0 function. Okay, great. That means that W is a valid subspace, and that concludes our proof. This is the last video in a series. I think there's 3 of them, so just to go over everything really quickly, I have a video covering all of the basics on what it means to be in a vector space, and like linear combinations and dependence and spans, which are all really key definitions for doing anything. I have a video going over some proofs, so how do you actually prove something? What's a general framework for doing it? And lastly, I have this example on functions and subspaces, because they work a little uniquely. I would recommend you all to go over all of the videos, all of the content on the course website, which is jackswitzer.com. There's notes on everything. I'm going to add some week 5 stuff here. I'm also hosting the EngLinks workshop on Saturday, 2 to 4 p.m. in Sterling Auditorium C. I would sign up. That link will be on the website too. And then similarly, there will be a help desk on Monday offered by EngLinks that I'm helping run from 6 to 9 in the ILC Beamish room 313, I think. This is all to say, you guys have a midterm coming up. It's on Tuesday. I'm pretty sure you have a couple other midterms, but don't slack on this course. This midterm should be very, very doable, and it's a very good opportunity to start the class off with a very good mark where you're going into the second midterm feeling a little more confident. I hope that this helped explain to you guys a bit on the intuition of what actually is a vector space. What's our notion of dependence? Please give me feedback on these videos. I know they're not perfect, but they're what I could do at the time. So thank you for watching, and goodbye.